Welcome to April 20th LeetCode Challenge, Binary Search Tree Iterator. Implement the BST Iterator class that represents an iterator over an in-order traversal of a binary search tree. The method binary BST Iterator takes in the function tree node called root, and initializes an object of the binary search tree iterator class. The root of the binary search tree is given as a part of the constructor. The pointer should be initialized to a non-existing number smaller than any element in the binary search tree. HasNext method is a boolean that returns a boolean or returns true if there exists a number in the traversal to the right of the pointer, otherwise return false. The next method returns a integer which moves the pointer to the right, then returns the number to the pointer at the pointer. Notice that by initializing the pointer to a non-existent smallest number, the first call to next will return the smallest element in the binary search tree. You may assume that the next method calls will always be valid. That is, there will be at least a next number in the in-order traversal when next is called. Okay, so given this binary search tree, here's an example. It takes in, let's see, a method call and the tree itself, and yeah, and returns. So the first thing we want to do is call binary search tree iterator function, which is null, and then you would want to do a next function, which is initialized to a non-existent number, which calls to the next smallest number, which is 3. If you call next again, it will be the next largest number, it will be 7. And then you want to call HasNext. So does it have a next number to it? True if it exists a traversal in the right of the pointer. The answer is yes, because we have 9 next, right? So then call next again, we have return 9. Call HasNext, does 9 have a next number next to the right of it? The answer is yes, which is 15. You call next, which returns 15. Call HasNext, which returns true because you have 20 next. Then you call next, which returns 20. If you call HasNext, 20 has no pointer, it points to null, so therefore return false. As such, the number of the node in the tree has a range between 1 to 10 to the 5. The value of each node is between 0 to 10 to the 6. Yeah. And most 10 to the 5 calls will be made to HasNext and next. Follow-up can implement next, HasNext, an average of 0 constant runtime, and the big O of h memory, what h the height of the tree. I'm not sure. Let's try it out. So they're following from this week's kind of model of binary search tree. You can use a stack as a base model or structure for this method, but I'm gonna try to use a double-ended queue. Let's just see how that will work. So to make our lives a little easier, let's initialize self.treeNodes self.nodes, I guess. I'll call it treeNode. TreeNodes to be a double-ended queue. Right? I mean, you could follow. Actually, let's follow last week's example. Yeah, I could do that actually. So get the in-order traversal of the tree node, the order of the tree node values. So we want to find another function called in-order, which is takes in root. Now, if not root, return an empty stack. Return, we're going to recursively call in order and we're going to take a root.left, concatenate it with root value, concatenate with root.right, or in order, I should say, root.right. Okay, the function. Oh, and then we want to basically return, not return, we want to update self.tree nodes to be in order of root, which calls the function. That should be good. Next thing you want to do is definition of next. Next returns true. No wait, moves the pointer to the right and returns the number of the pointer. So basically what we want to do is pop basically the smallest integer, so return self.tree nodes pop 0. Oh. We're going to update this a little bit later because this pop 0 is popping from the very beginning of the stack, which is not the best thing. That makes the runtime complexity quite long, but we'll deal with that in a bit. And then has next, we want to check the next value, if it has next value. So basically check if there's a remaining integer. So basically return, how do we do that? I mean, if we return the length of self, I guess, dot tree node, nodes, and that's not equal to 0. Alright, let's just check this out. Looks decent. Alright, accepted. Awesome. So this is using a stack. Not the best because you have to pop 0. Let's kind of modify it a bit to make it a little bit more neat, I should say. So instead of using a stack, let's just erase this. We are going to use self.tree nodes a double-ended queue. So this way we just easily pop from the front and define our in order traversal function again, which takes in let's see, let's do some node, let's do some type annotation as well, so optional. Tree node. Which returns none. So what we want to do is append the values of each node to the self.tree via in order traversal of the binary search tree. So if node exists, in order, call the method in order and do the left, and then self.tree nodes.append node.value. It's kind of similar to what we did before. We concatenated. Now we're just basically appending it because it's not a stack. It's a double-ended queue. Node.write. Alright, and then we want to do the same thing by calling it outside the function, call it in order, and passes root. Now instead of self.pop, what we could do is pop left due to the functions of a double-ended queue. And this should be good too, but let's just make this a little easier as well. And then we just do boolean of tree nodes. Basically, if it's a 0, returns false. If it's 1, return true. Run the code. Good. Accepted as well. Wow, this is actually a lot slower. Okay, never mind. I'll take that back. Alright, then let's go. Our previous approach was a little bit better. But yeah, that is all. Let's see. Is it average runtime of constant space? Yeah, I think so. Wait, no. I don't know. Alright. Well, that is all. Have a great day, guys.